Exercise 1718 is just making sure that you understand what it means for a conjugated pi system to be s-Cis versus s-Trans, and that the Diels-Alder reaction only works when the conjugated pi system is s-Cis. So we're used to thinking about double bonds as cis or trans. So a double bond can't rotate because you get it from the overlap of two parallel p orbitals. And if you were to try to rotate that bond, the p orbitals, one of them would stay still, the other one would rotate, and they wouldn't be parallel anymore, so you'd have to destroy the bond. But there's an energy barrier to doing that. It takes energy to destroy a bond. And so double bonds don't rotate. Well, imagine the scenario we have now with these conjugated pi systems. We have double bonds on the end, but notice that in these double bonds, you still have those parallel to, in these conjugated pi systems, you still have those parallel p orbitals in the middle, right? You predict these parallel p orbitals because of the pi bonds, but because they're conjugated, the two in between the double bonds, those are also parallel p orbitals, and so the electrons fly around that whole thing and form the molecular orbitals that we've seen. But what that means is that because you have two parallel p orbitals here, where you thought, you might think you have a single bond, because there are two parallel p orbitals here that electrons are flying through, that means that this bond is actually not just a single bond. It has double bond character because of the two parallel p orbitals between those atoms. And because of that, just like in the case of a double bond, that bond has a hard time rotating. Now it looks like a single bond, so they put the word S, but here it's really pretty much stuck in this orientation. It doesn't want to rotate, and so if you look to see what side the branches are relative down that sort of dotted line, here both of the branches are below it, so they're on the same side, so it's s-Cis. Whereas if you were to do the same thing with the other one, you have a line right there, that dotted line, that isn't going to want to rotate because the two p orbitals are next to each other, are parallel. So there's electron density flying through there. There's a partial second bond there that you'd have to break in order for the bond to rotate. And so if you look at opposite sides of that, or if you look at the branches coming off of that, they're on opposite sides of that dotted line, so you have s-Trans. So again, S because it looks like a single bond, even though it isn't. And then cis and trans because that bond does not want to rotate, because you'd have to destroy the connection between those parallel p orbitals. We saw that the Diels-Alder reaction only works if the lowest unoccupied molecular orbital of a diene, O-phi, is able to overlap with the p orbitals on the diene. But that can only happen in the s-Cis conformation. And you can see here that the two lobes can overlap there on the Diene-O-phi, which I'm moving around in this square, and the diene, which is s-Cis. If you try to do that same thing with the s-Trans, you'll notice one orbital will overlap, but the other one won't. So you can't get the Diels-Alder reaction in the s-Trans conformation. The LUMO of the Diene-O-phi just won't be able to reach the two ends of the molecular orbital in the diene. So s-Trans won't work for Diels-Alder. So already, you see this one in the middle, and you're like, this is stuck in the s-Cis conformation. That's great. That's the best you could have. The one right next to it is stuck in the s-Trans conformation. S-Trans. So that will never be able to undergo a Diels-Alder reaction. And this last one sort of on the right, this is an interesting one. It is in the s-Trans conformation right now. If you were to draw a dotted line down that seemingly single bond, you'd see that the two other double bonds in that conjugated pi system are on opposite sides of that dotted line. So it looks trans. It looks trans if you're tracking that seeming single bond there. but it's not necessarily stuck that way. If you heat this up hot enough, these bonds are going to jiggle and rotate and knock around, and you could get this to rotate. There's just an energy barrier. If you pump the energy in, it will eventually rotate, and so you could get the s-Cis conformation if that bond rotates. There's just an energy barrier to it, so it would take longer for it to happen because you'd be waiting around for the energy to get there. So they want you to rank these in terms of reactivity. This one in the middle is the most reactive because it's stuck in the s-Cis conformation. The one on the left is the least reactive. That will never undergo a Diels-Alder reaction. It's stuck in the s-Trans conformation, and of course the gray one is in between. And that's in between because the way it is right now, it's in the s-Trans, so it's not going to want to undergo a Diels-Alder. But if you heat it up, it'll rotate that bond. You have to heat it up a lot, though, so that'll take time. But if you do that, then it'll be able to react at least, eventually. So it's not going to be the fastest, but it at least could happen, which is not the case in this red one over here.